I want to test it.
What? So this is a sound meter, okay? And obviously it picks up the sound and then it gives a reading in decibel. So with everybody talking, there's a little bit of sound. You're right now pretty close to me. It's fluctuating between like 75 to 85, okay? And that kind of matches, if you look on this chart, busy traffic, that's like 70, vacuum cleaner, that's like 80, okay? Now, what I want to do is I'm going to yell into this, okay? And we'll see what the reading is. So, okay, so here we go. Ah! That hurt. And that got up to like 102.
That's not
Okay?
Oh yeah.
So,
Yeah.
that was basically a pneumatic hammer. Okay? At 2 meters away.
Yeah, that's easy to reference.
Yeah. Okay. So, but if I hold this away from me and I yell again, what should happen to the reading? It should go down. Why? I'm further away from it, right? So I have the same intensity of sound coming out, but that's going to spread out. So if we do this now, ah! So that only got up to like 99. Whereas if it was really close, I hope nobody was walking by.
102. I did see a silhouette.
There's nobody out there, but they were watching. They didn't hear a random.
So here's the point of this. Is that this is a function, whether it's sound, whether it's size, it doesn't make any difference. Any type of wave energy is going to decrease as a function of R squared. And with sound intensity, and again, you don't need to memorize this equation. If you need it for the test, I will give you this equation on the test. Okay? You just have to know how to use it.
It's on the test.
He's teaching too.
Okay.
You should put those decimals in there.
We got our fourth.
Okay?
Yeah, that's what I forgot.
So, this.
Are you sure? Just no, because it's like it will decrease as like a factor of R squared.
Okay. Now, does that sound, as that goes around, is there any change in sound?
Yes.
Sounds different. Okay? Change it. Let me.
It's different.
We should do an angular velocity and let it go. Right in the TV.
Okay? Can you tell the difference as that goes around?
Yes.
It's a little funny.
Okay. So this is what's known as the Doppler effect. Oh, I've heard of that. So, let me switch over to this camera, or this other television, and give you a second. Yeah.
Oh, is it actually not changing?
The closer sound is, the louder it is. Shannon, the closer sound is, the louder it is. It is actually, or it's not actually changing the sound, it's just the distance between the object is closer than far. That's why it sounds good.
Oh, so yeah, the frequency is not itself.
Okay. So
It sounds like basic. Like an echo. Oh my goodness, it's showing it.
Oh no, actually.
That's on video. Hey, in case you didn't hear it, Kayla Wynn is going to type
It was alive 5 million years ago. It's different. Your TV or
I think it's okay.
Oh,
That's not the answer. I still don't understand.
I'm pretty sure he said.
Wait, I can't hear it. I can't hear it.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
I didn't get it.
It's the apparent
Okay.
change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Stop.
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
And what are you supposed to be?
Me? I'll give you a hint.
Choo-choo train?
Close.
A brain damage choo-choo train? I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves? Because I'm Frodo. Yes, well, I'm the Doppler effect. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay. Once more. No.
That might be good. We need at least one more.
There's too much radius between the
Maybe we
TV
can put it
and
on a speaker with a card.
the frequency was too low for me to hear.
What would you get out over there?
It's supposed to be on the spectrum of hearing.
Yeah. How about like
No, but it's like an edit. It changes his some spinning images in the background.
That's like a race car. But you editing this stuff.
There. Listen.
The ones where it's like,
Listen.
Bro, why don't you guys doing the YMCA all the way back?
I don't know, he just said
did we see anything that could actually Oh, I thought that was like the left and right.
Is that 1 minus BS? That's a really long one.
Oh, that's one.
Yeah.
Name me a notable difference.
between animals when they are not speaking to each other and already
I know. How do you say free to play?
Do we divide it by sound?
Oh.
I don't know.
Okay. So again, this is like some weird one, and I will always give you this equation. You just have to know how to use it. So if you've ever watched the TV stations and the weather, they'll say we have Doppler radar. Okay, this is what they're talking about. Now this is kind of the simplified version of this. This is where you have the train coming towards you versus the train coming past. Right. So Vs is the velocity of the source. Now, it kind of works cool. Then you're dividing that by the velocity of sound. So if the source is stationary and it's not moving, what happens to the bottom? It just becomes 1, and the frequency that you hear is the normal frequency. Okay? And the same thing is true if it's approaching or moving away. So if nothing is moving, you're just going to hear the normal sound. So here's what we're going to look at. So let's say that we're going to have, in this situation, I had a frequency of 883. Okay? So the frequency of that tuning fork is 883 hertz. Okay? And let's say that the velocity of the source is, let's make an easy number, I don't know, maybe 20 meters per second. There's to be about 45 miles per hour. So let's say you're standing on the side of the railroad tracks and you have a train coming towards you and it's blowing its horn. So speed of sound, that's just going to be 343 meters per second. Okay, that's a fixed value. You're not going to change that. So if we want to figure out, this is going to be the frequency that you are going to hear. Okay, now mind you, this is coming towards you. So here's the train, you're standing here, okay, and the choo-choo train, thanks for that sound effect, okay, is coming towards you and it's emitting sound, all right? So remember, frequency is what you hear, higher pitch versus lower pitch. So if we want to figure out what you're going to hear, so we're going to take that formula by F naught, which is 883 hertz, all right, so we got that number. Then because of the fact that this is approaching, we're going to use 1 minus 20 meters per second over 343 meters per second. Okay? So you're going to take 20 minus 343. So just look at the math. You're going to take 20 minus this number. So what are you going to be dividing by a number bigger than 1 or less than 1? Less than 1. So what's going to happen to the frequency that you hear?
Way higher.
It's going to be higher than 883. Oh, it's getting closer. Because what's happening is that you can think of these as these wavelengths are getting crunched together. So as your wavelengths gets crunched together, and the speed of sound is a fixed value, so as your wavelength gets shorter, what happens to your frequency?
Increases.
It increases. So somebody do the math. What do you get out of this?
938.
938 hertz. Okay? Cool. Now, once the train passes you, what's the only thing that changes?
What?
Down here, instead of subtracting it, now we're going to add. Now you're going to be dividing by a value bigger than 1.
The frequency gets
and it
smaller.
should be less than 883. So if you do that math, I don't know what you get, but it's going to be less than 883. So NASA and what's called the Jet Propulsion Lab, okay, JPL, based in Pasadena, California. One of my former students was on the Cassini mission. So on the Cassini mission, they had, so here's Saturn, and here are the rings of Saturn. So they had to try and keep track of what this probe was doing, as the Cassini probe was doing as it was going around the rings of Saturn. Well, here's the problem. You had a whole bunch of things that were moving. Saturn itself was moving because it was orbiting around the sun. The Cassini probe was moving relative to Saturn. And here we are on the Earth. The Earth was spinning, and the Earth was moving in its own orbit. And we had to try and keep track of where the Cassini probe was. And what they did is they took very, very precise measurements, because the Cassini probe was always emitting, in this case, instead of sound, it was emitting an electromagnetic radiation, it was emitting a pulse. So when Cassini was approaching the Earth, it was like the Doppler effect. So when Cassini was approaching the Earth and that was spinning towards it, and here's the other thing that you had to keep in mind. Not only did you have to keep track of, is the Earth itself on its axis spinning towards the Cassini probe, versus if you're on this side and then that satellite receiver would be going away from the probe, then you had to worry about the Earth itself. Was it going towards Saturn, or was the Earth going away from Saturn? So you had to keep track of like all these different variables to try and keep track of where the space probe was. So this is the very simplified version. You're stationary, the train is coming towards you. But if you can figure out the differences in those frequencies, you can figure out the velocity. And the same thing is what they did with the Cassini probe. They said, oh, okay, right. So if the Cassini probe is going towards us, you would see a shift in that frequency. So the same thing happens with galaxies. So one of the how we figured out the galaxies and kind of the Big Bang is that they started looking at light that was emitted by these stars and these galaxies that were far away. So as they moved away, the light that was being emitted was being stretched. Okay, this is what we call red shift. So because the galaxy is moving away from us, that light, as it was emitted, the wavelength became longer because it was just a Doppler effect on steroids. But this is dealing with galaxies. So these galaxies are moving away from us. And the light is being shifted towards the longer wavelength, okay, because of the fact that the wavelength is getting longer because of the fact that it's going away. It's getting stretched out, okay, because it's going away from us. But here's the problem. This is what we're running into, is that the farther the galaxies are away, the more that they're accelerating. And the faster they're moving away, the longer that wavelength is getting shifted. So the problem that we're running into now is that some galaxies are so far away, the light that they're emitting has shifted so far outside of the visible spectrum. So we can't see it because now it was emitted in the visible light spectrum, but because they're moving so fast and they're so far away, now that light is being shifted into the infrared spectrum, and we can't see it because that light has shifted so far. So we're going to reach a point where there's some galaxies we won't be able to observe unless we look at them in the infrared because that light has been shifted. Now, the worst thing that it won't impact us, but now let's say the universe stops and it begins to contract. Okay? Now what are you going to run into? Now you're going to have blue shift. Okay? So blue shift, if we see that galaxies, their light starting to shift towards blue, now you're going to have, instead of the Big Bang, you're going to end up with the Big Crunch. Okay? And the universe will come back on itself, and basically it would be like a rubber band that will stretch, and then it comes back. Okay, won't impact us. We're gonna screw this thing up way before we get to that. Okay, I'm done.
They act like they didn't know that was coming.
Good one, Gavin.
Oh, freak out. It's a random thing of freak out.
Oh, brother.
Well, only.
No, don't ask that. No.
You were very.
We're up.
70. Oh, brother. I'm about done.
Work on this.
16. Oh, brother, one more time in my ear, Brad.
17,
Over into 20.
18.
17, 18.
Okay. So when you get to question 32, you need to go to the index at the back of the book, and that's going to give you the distances from the sun to the different planets. So don't Google it, okay? In the back of the book, there's a table that lists information about all of the planets and how far away they are from the sun. You also, on 32, want to use power equal intensity divided by 4 pi r squared. Because what it's going to ask you to do is find the intensity of light at different planets, Venus, Mars, and Saturn. Okay? So to get that information, don't Google it. Go to the back of the book. Now, let's talk about question 48. Okay? Or problem 48. So the first time that I assigned this problem, the kids were flipped out. Okay? So 48 is a Doppler question. It says an osprey's call is a distinct whistle at 22,200 hertz. An osprey calls while driving a huge, drives away from her nest. And the kids got so wrapped up, not in the math, but they didn't know what an osprey was. No, it's a true story. The next day, the kids came in and they said, Burkham, what is an osprey? We have no idea what this is.
An ostrich?
So what? Do you really think an ostrich is going to be diving at you?
Dave Mike.
Okay, I'm thinking osprey, so I'm like, I'm changing to ostrich.
Osprey. Does anybody know what an osprey is? What is it?
It's like, it's like a bird. Like
I think
wait, I got this. What else are we diving in? It's a bird, it's black and white, it eats fish.
Similar to
Yeah, it's a bird.
Penguin. It's a penguin. It flies,
Okay, that's Mick Jagger. We were talking about the lip curve today. The kids wanted to see a picture.
Like Jagger.
Did you all get the assignment?
No.
Bro, I got, hey,
I'll take a picture of it.
I got it.
I have it's like a 20.
Yeah, okay, I am. You are definitely on team with this, Ryan.
Sorry.
I'll rewrite it. I clicked out of the wrong thing.
Which one? Is it both? Yeah.
Oh, it's black and white.
It's at 49.
No, because I said a black and white bird that eats fish. I said it's black. The penguin's black. When have you seen a penguin black? No, I didn't know. I've never seen a penguin.
Look in here.
Where have you seen a penguin black?
Oh.
Hey, what did that No, we're following the style.
What does that say? 28, 30? 30? Yeah. Sadly. 38, 39.
4, 9, 4.
Whenever you watch it.
Which one did you say? 32.
And it's on 32 where you have to look at the
You get a good watch. You can watch it with me.
Yeah, last time I watched it with him.
I have to read it like.
No, I was watching it. Only when I watched it.
School on Tuesday.
Huh?
I think it's on A7.
Page what?
A7 on the end.
A7?
Yeah, we do Century 2 run. Rest of the Century 2 run.
So if you technically want to know where that information is, it's on A7.
And use what equation for number 32?
That the numbers for the area, you're going to use that
It's also this.
4 pi r squared.
Okay, gotcha.
Exactly what it makes sound to get that.
That's where that index is.
Still
that
probably
I-
get it.
Area 2 pi r.
You got this.
I just run into the small r squared.
No, it's just like it's not a circle, it's a meeting from the
You think Reese will be able to sit on it?
Huh?
You think Reese will be able to
Wait, do we gotta keep the camera on? It's just